Paulitsch from the University of Technology of Graz. For his presentation, he will talk about technical support for efficient hail mitigation, and he will talk about technical things such as WeatherRadar, analytics, the software that is needed for analysis, everything that is needed to plan hail mitigation, and also an overview of the Styrian Hail Mitigation Cooperative, and I know you will also explain to us how WeatherRadar works.
Thank you very much for this introduction. I'm happy to be here and be able to hold my presentation at this symposium. I am working with high-frequency technology, so I am also linked with radar technology, so I will also say something about this. Thank you also for substituting for your colleague. You have two presentations today. You have two presentations here today. So first presentation, please. So we are talking about, will be talking about technological devices to support hail mitigation. In 2010, there was an important change. A platform was put into place by the Department of Disaster Control of the Styrian state, federal state, and they made it possible for us to use to take the hail mitigation to the next level. The members of the hail mitigation platform are the hail mitigation associations. We had the Hail Air, which stopped operating in 2019, and now we have the Styrian Hail Mitigation Cooperative with 4 planes, and they fly over a large area in Styria. And the second company is Südflug with 3 planes. Other members are the Austrian Center for Meteorology and Geodynamics and the Austrian Hail Insurance and the University of Technology in Graz. So what are the goals of the platform Hail Mitigation? At its creation, we realized that we are not always very efficient in what we do, and we also don't have any cooperation between the various agents. So we decided that efficiency should be at the core of everything we do, and we also realized that we want to document our seeding activities. We also wanted to make weather radar and plane position data available for everybody. We needed to equip planes with mobile weather radars for this. Another important aspect and goal was to collect data and analyze data so that we can check, so that we can document how the hail mitigation system works. In order to do this, we had to build up a database and make an archive where we collect all data and where we can also analyze the data collected. And also have a statistical analysis, but also to evaluate the individual hail mitigation operations. I have made a diagram of the system. So this is what we've been building up since 2017. One of the pillars of hail mitigation are the weather radar data. Is the weather radar data, and then on the other side we have the displays in the airplanes with an online data transmission, and we also have, as a fourth pillar, the HailSys analysis program for hail data analysis, and we of course also have an operation central where we can see all the weather data and the plane positions. In addition to that, we have a data archive in our institute with all the weather data and the position details of the planes. We also get data from the Center of Meteorology and Geodynamics, and we are also in exchange with the Austrian Hail Insurance. In the next step, I would like to talk about weather radar stations in the region. One of them is operated by Austrocontrol. It is situated as at an altitude of, it has an antenna of 4.2 meters and works at 5.6 gigahertz and sends signals in two directions. It has a performance of 500 kilowatt impulsion and has an antenna of 4.2 meters, which means 0.95 degrees. Data transmission is done by radio via the Austrocontrol, and from there it is transmitted to us via the internet. This radar already exists since the late 70s, I think. The last upgrade, which was actually a complete renewal of the radar electronics, was in 2018. The other radar is in position owned by the Hail Mitigation Association. It is a Doppler radar, but doesn't have the dual pole Doppler function. It has a performance of 300 kilowatt impulsion and 2.4 meters antenna, which means 1.6 degrees. This is from a company in Slovenia, produced by a company in Slovenia. Data is transmitted by radio. It is from the year of 2001 and was upgraded in 2021 with new radar electronics. And it is now up to date. So we don't have analog data procession, but we have processing anymore. We have the latest state of technology now. How does the weather radar work actually? A weather radar is an impulsion radar. This means that there are short, highly frequent impulses, which then which are then propulsed into the atmosphere and reflected back at the radar. The radar receives the echoes, which serve to calculate the distance, and the intensity gives us an indication of the intensity of the precipitation. We have a number to measure this. This is Z, which is directly linked to the received energy, but also the distance to the radar. This figure Z has an interesting faculty. It is proportional to the diameter of the droplet at the 6th frequency. So the rain droplets actually have a strong effect on the signal we receive. So if we have a diameter of 1 centimeter, I would have the same echo as I have with of 1 million droplets of 1 millimeters. Another interesting fact is that this reflectivity is different by the factor of 5 if we have to do with ice or with water. Water reflects much more intensely. In order to depict this reflection, we use the figure dBz because we have a factor from -10 to +65, so we cannot actually calculate that in the usual way. So the radar itself wants to probe the whole atmosphere, so we want an antenna which can be moved in different directions and which can operate in different distances. A typical measurement, a typical resolution would be 1 × 1 degree per 250 meters. Our radar installations can be operated in various ways. So the radar on Reicherhöhe is different to the one on Zierbitzkogel. The radar on Reicherhöhe will do automatic 2D scans every 30 seconds. It's done either permanently or on intervals. Additionally, it is possible to do altitude scans. This means that the antenna is positioned at a certain altitude, and then it will swerve at this altitude and do an altitude profile at this level. So we have a 2-day scan. You can see that on the left picture with the white intersection line, and then in the altitude profile you can see the intensity distribution, which goes up to 10,000 meters. The radar on the Zierbitzkogel, on the contrary, is operated by flight security. It needs to operate 24/7, and it operates in with 3D scans with 16 elevations from -0.5 up to 60 degrees. So we have a complete volume of at the altitude of 16 kilometers, but it takes longer to operate than the 2D scans. The advantage of the 3D scans is that we have a better calculation basis in the software for the altitude profiles. So you can see this on the picture that I have, in addition, the altitude profiles directly here in the software. Now the question is, how can I detect hail with a weather radar? So we depend on the type and size of the precipitation particles. So we don't have enough information here yet. We need additional information, which can, for example, be altitude or the surface quality of the clouds, and also for dual radars, two differently polarized measurements. I would like to detail the Heidvogel method. He's a scientist from Switzerland who did research on radar and hail. And he realized if I have a reflectivity of more than 45 dBz at an altitude of more than 1,400 meters, then I have a high probability for hail. The background for this is that if I have hail on the ground, then the hailstones must have passed through the 0-degree zone. They melt, but if they are small enough, they melt. So if they reach the ground as hail, then they have actually been very big at a higher altitude. So this is what we can see when we have more than 45 dBz. This method is actually easy to apply because I can see the 3D data on the radar and then look at it at a certain altitude, and I can see straight away, do I have a hail or not? And you can see this picture at 2,500 meters. And this is a possibility for the operation lead to check whether we actually have hail probability or not. So this was a brief overview over the weather radar. Of course, it's also important that the pilots have this information. So this is why we have equipped all planes with weather radar displays. The displays give the pilots live information on radar data, but they also they also detect the flight positions, the plane positions, so that the operation lead can at any time control and see the positions of the airplanes. You can see, so the pilot himself or herself can see also the other planes' positions. So this is also transmitted, and these displays are really also for communication. So the operation target can also be projected directly on this screen. Also, all the flight movements are documented on this display and can then be used for analysis later. Barometric data are also transmitted, like, for example, the temperature of the burner, and weather details can be shown on this screen too. Mr. Josef Mündler also mentioned that in his presentation already. I would like to go into detail a bit with this display. We can see the second generation already here in this picture. Before it was the first generation, which we had when we first equipped our planes in 2009. Now we have an upgrade. We have larger displays. On this display you can see the weather radar data. The pilot can choose which area they want to look at, and if they want to have a 3D radar, they can also see the current GPS data, and they can see their own positions, their speed, their altitude above ground. And the altitude above ground is calculated via a digital model, and they can also see the positioning of the other airplanes. There's also the data, the GIS data, where the air traffic control actually doesn't have these details, but the pilots do have them. You can see the topography and the operation area. Here I wanted to show you the image that the pilot sees during the operation. So this is remarkable because we can see actually 6 planes in the air. So the plane we are flying is the white plane, and there's 5 other planes in the air. So this was an operation that needed a lot of planes, and you can also see that the planes are very close to each other, as Mr. Heidvogel already said. In order to make sure that nothing happens, they fly at different altitudes, so they have their attributed altitude in order to prevent accidents. So I can see the altitudes of the airplanes on the screen. So the pilots see the same as the air traffic controllers see. This is just for their own planes, not for other airplanes. And also this doesn't work 100% like with air traffic control, because we don't really have the possibilities to do that. We have a well-functioning radar data transmission, but there can be errors after all. We have a few data interfaces too, intersections too, where the pilot actually can can actually choose their plane and input coordinates and send them. So this is the list that you can see on the picture in the middle. So the pilot would then get a message saying this plane needs to go to this area, and they also get the position immediately. And then the pilot can confirm, so that the operating lead actually has the confirmation that the pilot has seen the order and is going to the designated spot. So we are using the coordinates of the operating areas, so the operating lead and the pilots use this map. The operation lead also sees where the planes are going at the moment. So this is the weather radar plus the position details of the airplanes. So here we can see 2 airplanes. One has the tag seeding is on. This means that they are seeding already. The other one has the burner switched off yet. So by this picture, by this image, the operation lead can see where planes have seeded clouds already. Planes can fly a long way during operations. Here we can see flight routes, flight trajectories from the 29th June 2020 and on the right the 21st July 2020. So you can see that in July we had 6 airplanes in the air. So there are so many planes that they actually don't fit on the status line on the bottom. They flew from the Slovenian border to the borders of the Burgenland, so really to the borders of our operation area. An important point for hail mitigation is data documentation and analysis. So we have built up a large data archive which exists since 2009 and is worked on constantly, and we also have a radar data archive which dates back until the year 96. Which data do we have here? We have the radar data, we have satellite images, we have GPS details, we have seeding information from the operations, and we have more than 1 million data points already to this date. Approximately 1,700 days of operation we have already documented, and approximately 300 operative hours per year. We also have the data from the Austrian hail insurance, and also hail test plates, test boards. We also have hail monitoring data from various platforms, and we also get details from the Center of Meteorology and Geodynamics, of course. So this is an interesting program, the analysis program of HailSys. We can see the radar view, and using this, we can also look at seeding information, flight trajectories, and also damage information, damage reports. We can analyze cells, thunderstorm cells. We can do calculations and along the trajectories. We can find out vertical integrated liquids or kinetic energy, which results from hail. We can use Waldvogel criteria. We have the possibility to also do other graphic depictions. We can depict damage reports and seeding activities.
So here we see an analysis of a trajectory and its parameters. So I have the parameters, and they are shown here in two curves. One parameter is from the hail criterion according to Waldvogel, and the other one is a seeding activity. And what we see here is that when the criterion increases, the seeding started, and the longer seeding continued, the hail criterion declined. And this is what this map here shows. And then here an example of the visualization of damage, hail damage. This is the data that is shared with insurance companies. And this is anonymous data. And this is a comparison here of the years 2020 and 2021. And you see the frequency and the severity of damage is comparable. And as we can see here, over the past few years, the frequency has remained stable, more or less. Another item is the visualization of damage. And this is from our HEDI project, where people can report hail events, and these events are then visualized. This is a comparison left 2019 and right 2020. And of course, the hail events can also provide interesting statistics. For example, the question, at what time of day is hail most frequent, and how big are the hailstones? We use the ESWD data for the years 2010 to 2015, and what we see here is a distribution according to time on the left. So normally the frequency is highest between 2 and 4 p.m. But we can also see that there are hail events even late at night, after 10 p.m. or even in the morning between midnight and 2 a.m. And In the mornings, there are no hail events. This is also something that we know from experience. There's hardly a hailstorm in the morning between 8 and 10 in the morning. And another visualization here is that of seeding and the time spent per square kilometer. And yellow is approximately 80 deployments per year. And of course, you see that frequency is highest in the surroundings of Graz Airport, because the most flights take place there. I mentioned kinetic hail energy. This is an interesting parameter that can be calculated from the radar data, and it indicates the risk of damage that hailstones have when they hit the ground. And this is in connection with the hail impact boards that we have here, because these boards also measure the energy on impact. And by means of kinetic hail energy, we want to have the same information. So we want to see the energy per square meter, and if we compare this then to various types of vegetation, we can say or define the level of severity of a hailstorm. Here we have an example of the 25th of June 2021, the flight routes and the kinetic energy. And what you see here and what is most striking is that the highest kinetic energy was measured in these red and yellow areas, and this is precisely the areas where there were no hail defense flights. So one conclusion is that kinetic energy was reduced by the hail defense flights. So this is the last slide that I have here in my first presentation, and I'd like to thank you for the attention.
Fragen gibt,
Thank
dann
you.
wäre es möglich, eben wie gesagt, die über
As you said,
gleich zu stellen, beziehungsweise
you are now open to answer
Ansonsten
questions.
haben wir jetzt einen etwas geänderten Zeitplan.
We have changed our time schedule slightly. We are a little ahead of time because all the speakers are so strict, keep strict to the allotted time. And the idea was to have a break in half an hour, but we will have a break now. And so if you all agree, there are no questions at the moment. If you all agree, we break for coffee now until 15 minutes past 3, and then at 3:15 we continue with the final part, namely the coordination of steer and hail mitigation flights and a technical presentation. But first, let's break for coffee. There is cake and coffee available here, and if you are at home dialing in from your office or your home, maybe take the time to make yourself a cup of coffee or tea.